Thank you. Thank you. Good morning. Okay, now we want to switch gear from how we do AI on the ground to how we do AI up in the air. The I'm going to talk about AI application for development of flight functions. I'm with Acubed, that's an innovation center of Airbus, located in Silicon Valley. Airbus, large global company. In a nutshell, we build things that fly, large airplanes, helicopter, spaceship, rockets, you name it. And for me as an engineer, flying has something magic. You go to San Francisco airport, get in an airplane, and in a few hours, you're any place in the world, New York, Tokyo, Frankfurt, Paris, you name it. And this industry progressed so rapidly from something that was really only affordable to a few people to a democratization availability that is really astonishing. What is an aircraft? So an aircraft is, not to go into detail, is one of the most complex technical things ever done by human mankind, only superseded in complexity by spacecraft. And complexity. What's an essential part of aircraft and the safety related in aircraft? That's a pilot, so that's a very skilled individual that ensure the airplane gets operated in any condition, globally, any location, daytime, nighttime, you name it. And it's absolutely repeatable, safe, and robust. And that's also a feat of human intelligence. What's ahead for the industry? Right now, we have about, or an Airbus aircraft lands and takes off about every 1.2 seconds. I mean, picture that, every 1.2 seconds. We look at a tremendous growth in the industry. The passenger volume is expected to double from currently 4 billion passengers to 8 billion passengers. How many people are 8 billion passengers? That's about the population of the world that flies, expected to fly every year with our aircraft. So with that increase in volume and traffic comes also an increase in complexity. It's actually a nonlinear increase. And we focus on developing the technical means to ensure that the industry can handle that amount of growth, number one, and actually that we have an increased level of safety when flying. Good. One application area for AI is vision-based aircraft functions. So similar to autonomous cars, the approach is also for aircraft to look at vision as one means to understand the environment. And roughly to break it down into flight functions, you start with taxiing. It's basically a big car that drives around in the ground. That's not too difficult. Then you move to takeoff and then a few hours of something. And then comes the interesting part, approach and landing and obstacle detection. Now, the areas on the right, they're particularly interesting in anything on the left, like taxi and takeoff, we can abort and can decide not to do it. Once in the air, you have to go down, any conditions and whatever it takes. So particularly the approach and landing, that's a very, very formidable problem. Then obstacle detection, that ties into the area of outlier or corner case detection. The autonomy is easy. In normal case, autonomy is really, really difficult if you look at unexpected conditions, such as shown here. It's particularly for the corner cases, it's not that simple to even come up with an engineering specification. Now let's look a bit more into the topic of approach and landing. So how hard can that be? Well, if you have a really simple airport as shown on the left, It's actually not too difficult. It's picture perfect, lined out. You can see everything. It's only one runway. That should be easy. In reality, it's a bit more involved. So this is one airport in Chicago. It's basically a pile of spaghetti of runways. And it really makes a difference if you land at the right runway or you accidentally land on the highway, etc. That makes a mess, as you can imagine. Now add to that different weather conditions, such as our beloved San Francisco fog, where you see nothing or next to nothing, and then snow. So suddenly the world looks totally different in snow, basically an ocean of white, or look at nighttime, it's an ocean of blinking light that the pilot sees. So you need a level of robustness that brings me to AI. AI is, or particularly machine learning, is a technology that gives us the level of robustness that we would need to have both perception and decision-making working reliably under those conditions. So how do we develop AI functions for flight application? Let me start with what is our development environment. Well, naturally, it needs to be an airplane. And so on the right side, it's one of the test aircrafts that we have. That's an Airbus A350. To put it more into numbers, that's a huge beast, 280 tons weight. And just to put it in perspective, a car is about 1.5 to 2 tons. That thing is big. It can fly about 300 passengers. And most interestingly, as a test bed, it's about $1/3 of $1 billion in cost. So that means there are all type of requirements how we develop software, translating into relatively slow iteration speed from software to testing on an aircraft. And that's why we developed in kind of surrogate aircraft that's shown on the left that we operate here in Silicon Valley. It has a similar sensor setup compared to the large aircraft. It can fly some of the missions similar to a large commercial aircraft and allows us to do a rapid iteration from software development to testing, is similar to what you have in the software industry. The development process, we utilize what's called the data-driven development process. You start with a data set. And the interesting thing here is, compared to autonomous driving, where I can buy data from a ton of different companies, you cannot buy that. It's actually incredibly expensive and difficult to collect data. So we developing the means to do in rapid data collection globally. Then we utilize that to develop machine learning algorithms. The specificity here is our video feeds are really big. Say you deal with 20 or 25 megapixel cameras. Most of the algorithms they develop for other applications, they just don't work in this type of environment. Then we move to verification, validation. So we have super stringent security, safety standards, design, insurance, etc. That's a big topic. And then look at deployment. Deployment is also interesting because we're not operating these AI algorithms on a data center. It's operated on something that flies, and it's highly safety rated. So there's a tight link between how we develop algorithms and how we can deploy that on a specific safety rated hardware. And then lastly, there's a topic of certification. So we operate in a safety-rated environment. Certification bodies such as the US FAA or EASA in Europe, they sign off on any of the development, particular for aspects of safety. And so data-driven development, that means we start with a limited application area and then step by step expand the operational envelope and the capabilities. So important to say this is not a Terminator type self-learning system. There are a number of discrete steps, and what's deployed on an aircraft is in deterministic system in a sense. That shows an example of vision-based detection of runway features. So imagine you're about a couple of miles out from the airport, and you need to know, where am I? Where do I have to fly? How far? And it's basically establish a 3D relationship between where you are and where you want to go. And so you need to, in this case, identify specific runway features. And the output is basically a control signal, fly left, right, up, down. And also shows how difficult things could look like if it's daytime or nighttime. At nighttime, it's basically an ocean of blinking light. And it's actually surprising how robust these AI algorithms are, that they can handle that. And what didn't show you is how this thing looks like with fog or snow, etc. It's for someone who have worked for many, many years in computer vision, it's surprising how robust those AI algorithms are. The testing. So we need to do a very, very slow testing for the topic of design assurance, understanding what are failure cases, etc. So we invest a lot into synthetic data generation. So that's an example of synthetic data that we created. There are worldwide about 2,500 airports. So what we need to be able to do is to have a synthetic model of any of these airports. And now imagine you fly towards San Francisco. It's an ocean of structure, mountains, houses, highways, cars, lights. That just the sheer level of complexity that you have to do this type of automated model extraction. And we use mix of satellite data, ground data, etc., from multiple data sources, then to create these synthetic models, and then tie that into an automated test case generation, automated failure case injection, etc. You name it. That's a super interesting area. And why do we need synthetic data? It is A, to have just the data diversity that we need to really do testing, and B, is also a cost topic and a safety topic. So a lot of failure cases, such as cross traffic or, I don't know, a fire truck on the runway, you really don't want to test with an aircraft. Almost the only way to do the testing there is with synthetic data. Okay, to conclude, the AI is a key element to enable the tremendous growth that we have in this industry, the continued democratization of flight, and also the expectation of the public that it's safe and actually safer with the years going ahead. The magic of flight, it's a super interesting time to be in that industry. And I particularly like this combination of AI, software topics versus physical reality. And yeah, it's an interesting time to be in that industry. And I conclude with a shameless pitch. We're hiring. We're located in Silicon Valley, and we look for all type of good engineers. Thank you.